Hey everybody, welcome to Fluids Using Houdini. My name is Spencer Leaders and I'm really excited to teach this course. We're going to obviously be learning about fluids, but we're also going to learn about the components and the low-level concepts which are used to create, manipulate, and drive fluids, volumes, and I think it's going to be a great course. We're going to cover a lot of material. A lot of it will be new to, I'm sure, many of you. We're going to get into some very technical stuff. But, you know, I think we're going to do this in a way that hopefully everyone will be able to keep up. As this is pretty technical stuff, it's going to take some longer than others to learn the concepts, and that's totally expected. So please, on the forums, do not hesitate to ask questions. We're all in this together, so you know, let's utilize everyone and try to get the most out of this. So with that being said, we're going to just go ahead and jump right into what is a voxel, what is a volume. We're going to create a sphere, and let's jump in. Typically, whenever I am developing anything, I always start with basics. Spheres, cubes, grids, because you can iterate quickly on it. You can make refinements easily rather than trying to develop on something extremely heavy. And so we have our sphere. Let's turn this to a polygon, and we'll just set our frequency to 20 just to give it high enough res. Then let's create an ISO offset node. We're going to turn this sphere into a volume. Magic, right? Okay, we've got an empty box. So I'm going to do a couple things. I'm going to turn my construction plane off, and then I'm going to hit the D key to bring up my display options and go to the background tab. Change my color scheme to dark just so we can better see our volumes. But as you can see, we still don't see anything. So the reason is I am in wireframe mode. Hit W key, you're now in smooth shaded. That is something to remember whenever viewing volumes. You do have to be in the smooth shaded mode. Now right now this is supposed to be our sphere, but you can see it's pretty coarse. We have this stepping nature, tumble around, it just is really low res. Well, on the ISO offset we have this uniform sampling, and this defines the resolution of our volume. So we will say type in 50. Automatically we get a much nicer defined sphere. Now I'm going to take a step back and actually explain, well, what is this volume? What is a voxel? That word I've thrown out there. Again, some of you may already be well aware of this stuff, but for others where this is new, well, I'm going to explain that to you. Is that what this course is for? So what is a voxel? A voxel is a value represented in three-dimensional space. It's a single value, mind you, and it's configured in a grid-like pattern. A bunch of voxels create what is called a volume. Okay, now there's a few different words to describe a group of voxels or a bunch of voxels together. One is just the standard volume. Another might be field. Another is buffer. I'm sure there's a few others out there, but they all generally mean the same thing. You might find me using them interchangeably, so I'll try to be consistent, but you know, just as I'm talking, I might refer to something as a volume once and then a field. Right, so this is actually made up of a bunch of voxels. If I middle mouse on our ISO offset, we can see we have 1 point, 1 primitive, 1 volume. Now this volume resolution is 50 by 50 by 50. That means it's 50 voxels in X, 50 voxels in Y, 50 voxels in Z. Now 50 times 50 times 50, or 50 cubed, is 125,000 voxels. So there are 125,000 voxels which make up this sphere. If I go to wireframe mode, we can see all these voxels live within the bounding box here. This is the domain of our voxel grid. Now I said that a voxel is a value represented in three-dimensional space. Well, you might go, well, hey Spencer, isn't a point or a vertice a value represented in three-dimensional space? Well, yes, you're right. Okay, let's create a box. We'll just make this 2 by 2 by 2, just so it's the same, roughly the same size as that guy. Well, a point, turn our point numbers here. Each point, it is a value represented in three-dimensional space, but this point does not have any spatial representation, whereas a voxel does. Now the other thing too is this point has a coordinate, where voxels do not have coordinates associated with it. A voxel's position is relative to other voxels in our defined domain. The domain is the bounding box of our sphere here. So if we wanted to create a volume from scratch, right now we're creating this volume based off a sphere. What the ISO offset is doing is it is figuring out which voxels live inside the sphere and which live outside the sphere. And it's doing that based upon this mode, ray intersect. So it's firing some rays, figuring out the interior and exterior of the sphere. Anything on the interior, it's by default just giving a value of 1. If it's on the exterior, it's giving a value of 0. If I were to create a volume on its own, but if I go into wireframe, we can see we do have a cube. So we do have a domain, and the size of this domain is defined over here. If I set this to 2. But again, it's empty. All the voxels have a value of 0. Now if I were to set the initial value to 1, we can see that every voxel now gets a value of 1. Turn to 50. This is just an intro to what volumes and voxels are. Continuing on our exploration of volumes, voxels, we created a volume from scratch using this volume SOP. We're using an ISO offset to create a volume which represents the inside of the sphere. Now these are using both Houdini's native volume tools. And I know that because it says 1 volume. Now there's another way to create volumes in Houdini, and that's using VDB. See, there's a volume menu which has a variety of tools for creating and manipulating volume data. There's also VDB as well, which is another flavor, so to speak, of volumes. VDB was developed by DreamWorks, and it's an open source volume tool set. Houdini now is using this to create volumes. Now the benefit of VDB is that it creates volumes incredibly efficient, whereas Houdini's volumes are a bit slower. There's some fundamental differences as far as how the volumes are constructed, which make VDB much more efficient. If we wanted to turn our sphere into a VDB volume, we can do VDB from polygons. If I plug this in here, okay. And for the sake of just being consistent, let's uncheck distance VDB and check on fogged VDB. So we're comparing apples to apples, so to speak. Now they're similar. If we middle mouse, 1 VDB, whereas this is 1 volume. The other differences though is the resolution setting. In VDB, it is defining the resolution based on what you want the voxel size to be. Now this is in world space units, so 0.1 means that each voxel is 10 centimeters. Because in Houdini, 1 unit equals 1 meter. So this means there's going to be a voxel every 10 centimeters. Where this is just completely arbitrary to the the grid size. It means there's 50 in each dimension, whether the box is this big or if it's 5 times bigger or 5 times smaller. It doesn't really matter. You're always going to have consistent, uniform 50 by 50 by 50. Now we can change on our ISO offset just so we can make similar comparisons to VDB with Houdini's native by setting it to by size. So if we do 0.5, that took 189 milliseconds to compute. Where here, if we turn this to 0.5, that took 105 milliseconds to compute. If we turn to 0.1, that took 581 milliseconds, so almost or a little over half a second. Whereas if we set this to 0.1, still waiting, still waiting, still waiting, still waiting, still waiting. All right. Finally. Okay, that took 23.5 seconds to create a volume resolution of 8.5 million voxels, where this took half a second of 4 million voxels. Well, we both have their size set to 1 centimeter per voxel. What it's doing is VDB is throwing out any voxels that have a value of 0. Any empty voxels, it just discards. When you can use VDB, I strongly suggest it, because Houdini's native volume creation can definitely slow down the process. VDB also comes with this node called VDB Visualize Tree. Put our display flag on it. What this gives us is a way to view what our voxels look like. I'm going to actually, just for viewing purposes, okay. So right now we have these various cubes that are pretty big. These actually are not the voxels themselves. These are actually showing how it's dicing up the sphere, and then within each one of these cubes it processes and gives us the voxels. So this is showing that tree for how it's chopping it up. To actually see the voxels, we can go active voxels. We can view the voxels now as points. So each point represents a voxel. This will copy the values to the points of the voxels, and it stores it in this attribute called VDB float. So that gives us the value of the voxel. We can see wireframe box, and so this is actually showing the spatial dimension of each voxel. So if I set this to solid box, we can go to flat wire shaded. But you can see each one of these cubes is a representation, a volumetric representation of how much space each voxel takes up. If I were to turn this back to 0.1, the other thing I want to note, and I'm going to note this especially once we start getting into simulations and such, is when we double our voxel size, so we go from 0.1 to 0.5, we are not doubling the resolution here. We are actually increasing the resolution by a factor of 8. The reason for this being is when you double the resolution, you're doubling it along the x-axis, the y-axis, and the z-axis. So you're essentially doing 2 cubed, and 2 cubed is 8. So just be in mind when you're adjusting these values, right now we have 33,000, and now we have 4,000. So 4 times 8, this number times 8 is going to be, you know, roughly 33,000. Now we need to start exploring how to manipulate the data. We need to manipulate how the volume is created. We're getting a sphere, which is well and good, but we need to be able to do a bit more with spheres. So I'm going to talk about how to apply noise to a sphere. Now initially you're probably thinking, if you haven't done this before, well, that's pretty 101 stuff. You're correct when we're talking about applying noise to a polysphere. So if we were to create some noise, I'm going to create a VOPSOP. I do a lot of my work inside VOPSOPs, and that's how we're going to be doing a lot of things in this course. So if you haven't used a VOPSOP before, what this is it allows us to use a VOP context to manipulate our data, and a VOPSOP manipulates point data. So we're going to jump in, and inside the VOPSOP you have your global inputs such as position of each point and some attributes. If they exist, it'll bring them in. It doesn't create these attributes, it only allows you to bring it in, manipulate it, and then the results you can feed out, whether you're manipulating position, the normal, the color. You're not restricted to these global inputs or outputs. These are just the most commonly used, so they give you, they give them to you just so you don't have to pull them in manually. So to create some noise, we can just create a turbulent noise VOP. Now, noise requires a coordinate for you to look up, and we'll just say 3D noise. So it's going to give us, it's going to output an X value, a Y value, and a Z value at the given coordinate of each and every point. I'm going to add this value. Now, alligator noise ranges between 0 and 1. Original Perlin noise is between -1 and 1. So plug that. We want to add the value between -1 and 1. Add that to our position. And we plug it there. And we don't have anything. There. Got to put the display flag. So we've got our noise being added to the position of each and every point here, and we're getting this distorted sphere. I said we're going to be using VDB primarily, but for the sake of learning, we're going to go back over to our ISO offset, and I'm just going to turn that resolution up. So we've got our sphere, and if we were to plug this in, nothing is happening. We don't have a points to modify. We have voxel data. So if we're going to manipulate voxel data, we need to use a volume VOP. Here we go. Now we see this yellow warning flag. If we middle mouse, it says, oh, you guys probably can't see that. Pull this up. There. Okay. It says cannot find primitive attribute name, binding volume as density. Now what does that mean? Well, every volume, every field typically gets assigned with a name, whether it's a velocity field or a density field, a heat field, temperature field. Typically a name is assigned to it. That's a way of differentiating one volume from another, similar to attributes on primitives or points. Well, we need to do that with the volume. If we middle mouse on our ISO offset, we can see we have our first volume here is 0. That's basically the primitive number, colon, and then it just gives a resolution in that. It doesn't actually have a name associated with it, because we left that blank here, name, so we're going to type density. And if we middle mouse now, we can see it's now given this volume the name density. So now when we go in here, that warning disappeared because it does see that this name density is stored in the name attribute. So let's dive in. And we see that we have global inputs and that density is being brought in, and then it's just being fed out. Well, if we wanted to add some noise to our density, so P is just the location which we're going to sample of each voxel. And if we want to do similar to how we did it on our geometry, where we just added noise to each and every point, well, that's not quite having the same effect. If I were to turn this up, and let's change the noise type to Perlin. Oh, let's turn the amplitude up, say 10, or turn the amplitude up to 5. What we're doing here is we're adding noise, we're adding a value. In this case, Perlin noise is between -1 and 1. We're adding it to whatever the voxel value is. So voxels which have a 0 value is just adding whatever this value is. This sphere had a value of 1. Well, it's just adding whatever the noise value is. So you can see every single voxel is being affected. Whereas over here on our sphere, every point's being affected, but the point is only located on this outer shell. Everything else is around it is hollow space. It's not defined by anything. So that is a fundamental difference between dealing with a voxel grid and manipulating point data. So how do we do it so we only want to modify the volume data that currently exists, okay, that has a value that isn't 0? So we have to think about this a little bit differently. We want to only affect where there's value other than 0. So we're going to introduce this volume sample. Okay, what this is you give it a position. Based on the given position in world space, it's going to return the value of that voxel. So if I were to just plug this in, it's going to return us our sphere. It's no different than doing that. Whoop. No, not that. Density. Well, we can modify our sample position. If I were to put an add constant, so it's adding 1. So you can see we're offsetting the location in X, Y, and Z by a factor of 1. The other thing we can do is we can use noise to modify our lookup position. So if we put P in here and plug that into sample position, all right, we have a kind of band look now. Well, we need to change this to 3D noise, so it has an X, a Y, and a Z. Now it looks fairly similar to what we had before, but that's because our amplitude is cranked up quite a bit. If we turn this back down to 1, you can see now we're getting more of a cloud-like pattern, and you can modify frequency or what have you. So let's review what I'm actually doing here. Okay, so we have a circle, our sphere. When we plug it in that volume sample, it's sampling what the volume value is, and it's returning it. So here it'd be 0 all the way up to here. Here it's going to be 1 and everywhere inside. Well, what we're doing now is we're applying this noise, we're adding this noise to the given position. So this point here is now, this sample position might now be out here, depending on the amplitude. This point here might be out there. This point here might be out there. This point here might be out there. This sample point here might be out here, and so on. So if we take our volume VOP here, I'm just going to copy and paste, and plug our VDB into it, okay, it's similar, but this one sure has more kind of range and variation. So we need to actually expand our bounding region so it can look up, because right now the noise is looking up outside of the bounding region, and therefore it's returning nothing. So we do a VDB activate. Some of the names of these things, it took me a while to kind of track down where I can do certain things, and well, this allows you to specify certain regions that you want to do things to and manipulate the volume. The VDB activate, there is this expand, and this is how many voxels do you want to expand the bounding region. So if we put 25 in there, you can see now that we do have more range. And it's very similar to what our ISO offset. The density values are slightly different, and again, there is a slight variation to the way these volumes are constructed and what they're doing at the edge of the geometry that it's creating the volume from, things like that. But you know, generally speaking, it's about the same. So we've got our little cloud here.